Before we finish off this topic on thermodynamics with one more calculation idea, I want to get into the concept of Gibbs free energy and work and what exactly is the quantity delta G is capturing. The question is, what is free about this energy, right? Why is it not just called the Gibbs energy? And the reason is because if you look in that delta G equation, again, it relates delta H with delta S as a function of temperature. So what it's telling you is that delta G is the difference between what is possible, which is what's given by delta H, and that's energy from your chemical bond, right? And what is required by nature to be lost. And so that's your delta S component. That's lost heat. And remember that that's how originally in the study of heat engine is what entropy change was captured as. It's basically the amount of heat that is lost that we cannot use to do work. If you recall, the setup of that heat engine is you have something with a high temperature that is generating heat. So we call that Q at high temperature. And what we want to do is take that Q and basically make it 100% work. But what was found after trials after trials after trials is that it's not possible to make that happen, that there's a certain amount of heat that's lost, and we call that QC, and there's some quantity of it that goes to work. So it might be, 70%, 30%, it might be 60%, 40%. It depends on the specific engine, but never is it possible to take 100% of the heat being generated and convert that to work. And so that's what entropy originally is. It's a quantity that captures the QC. So this work then is what delta G is capturing. So delta G is just the maximum useful work that you can get out of a particular engine or a particular setup of a chemical reaction. And so we call delta G W max or maximum work. It's the case with heat engine, but it's also the case with electrical system, as you'll see in a future chapter on electrochemistry. Now, the other interpretation of delta G is for non-spontaneous processes, it is the minimum work you have to do to make that process happen. So again, if you get a delta G that is positive, it's basically telling you that at least you have to do that much work to get that chemical reaction or that particular process to happen. Let me give you an actual example of how to visualize delta. So this picture right here shows a battery that is being used to turn on a light bulb, right? So we just connect it in an electrical circuit, and we can see that when it's connected correctly, the light bulb will turn on. Now, how does this work? Well, there's electrons coming out from the negative end of the battery, and it's moving towards the positive end of the battery. So the electron is just moving based on electrostatic law. Now, as it's moving, anything that's moving has kinetic energy, so that energy could be converted into work. And the work that's done here is the work to light up that bulb. And so we see light, which is another form of energy, right? But what's interesting here is that just the movement of the electron, you would think that that could capture all the kinetic energy that the electron provides from the battery. But it turns out that the light bulb actually doesn't really get all the energy from the electron. The reason is because just by moving, the electron generates some friction in that material. So this is a picture of how that friction is lost through the wire. So for example, if you imagine these green little dots as electrons and they're just moving around the wire is brownish cream looking color. So the electron is moving here, but as the electron is moving, they're colliding with each other. And so as a result, friction is generated. And so that friction is lost to heat across the wire. So if you touch a wire, if it has a lot of electricity, if it has a lot of electron moving, you can feel that it's warm. And that's because that heat is lost. And that heat that's lost is no longer able to be used to light that light bulb, right? To generate that work. So therefore, there's always a quantity of energy that is gone, regardless of whatever system you set up. And that quantity that's lost is your change in entropy. That's what makes the process possible to do. Any process you do in our universe always has this cost of entropy, okay? And so if we look at a lot of the different types of engines or appliances that humans have created, actually what's interesting is that we're not even able to design things that are able to capture 100% of that delta G. Again, remember that the delta G itself is already less than 100% of the available energy, right, which is given by delta H, that energy in the chemical bond. Delta G is sort of like a universal requirement that you can't get 100% of the energy. But the engines themselves get even less because the engineering of these engine, design of this engine is such that they're not able to capture 100% of that delta G, that useful work. So here's just some examples, some numbers here to give you a little bit of an idea. Like that incandescent bulb that we used for a long time, now it's finally been taken off market. That's only able to convert 7% of the energy from the electron flow. That's 7% of what is possible. Okay, so it's a lot less than what the delta G allows. Electrical generator is a lot more efficient. It could take 95%. But you can see that some of these things are not really that efficient at all, right? They're not designed that well, in other words, okay? So that's just something to keep in mind about what delta G actually tells you. So to summarize a little bit on how delta G relates to work, when we have a spontaneous reaction, which is when your delta G is less than 0, your reaction will be able to do work on the surrounding, and that is the maximum amount of work that you can do. But if you're talking about a real machine, which is machines that we design like this, the actual work done is almost always less than that maximum work, just because the design itself is not able to capture all of the work that's provided by the delta. If you're talking about a non-spontaneous reaction where your delta G is positive, then that's a reaction that will only happen if you put in at least that much work, the work quantity that is equal to the value of the delta G, okay? And then if you have delta G equals 0, then that tells you that your reaction has reached equilibrium and that it's not able to do any more work. So in fact, a battery like this, as we'll talk about in a future chapter, is actually a chemical reaction that is put in a compartment, and then that chemical reaction has a certain delta G. The delta G is negative when the battery is new. But as you use the battery, as this electron flows from the negative side to the positive side, the delta G value gets smaller and smaller, and eventually the delta G is equal to 0. And when delta G is equal to 0, then the battery is what we call dead.